Video lecture from yesterday started on chapter 9, and we're only going to look at subsections 9.1 and 9.2 in this chapter. Today's problems relate to section 9.1, but the basic premise here is we're moving from a paradigm of looking at a single sample from a single population to looking at multiple samples from multiple populations. And chapter 9 is in this intermediate space where we make a slight extension, looking at having two different samples from two populations. But then we'll extend that even further. So once we move past chapter 9, we'll look at ways of dealing with, an arbitrary number of populations. But chapter 9 kind of just extends the idea of a z-test and a t-test going from a one sample setting to a two sample setting. So let's jump in and look at this first example problem. Here we're looking at an experiment that was set up to compare the yield strength of two different types of steel, cold rolled steel versus galvanized steel. The research team collected two independent samples, and in everything that we're going to be doing, the different samples obtained being independent is a very important assumption. So, however the sample of cold rolled steel is obtained, that should in no way influence or be affected by how the sample of galvanized steel is obtained. Those need to be completely independent of one another. In the sample then, 20 cold rolled steel specimens were taken, 25 galvanized steel specimens were taken. The average yield strength for each kind was recorded. And then importantly, we are told that we can assume normality for both types of steel, and the variances are known. So normality plus known variances, that tells us that we can use a z-test and that the z-test will give us exact results. So of interest here is, if we read part A, testing the null hypothesis for no yield strength difference against a general alternative. So the null hypothesis is saying, on average, there is no difference between the yield strengths. So we are saying we want, if I let mu1 and mu2 denote the average yield strengths in the populations, this is what we're after. We want average yield strength to be the same. Now, whenever we formulate a hypothesis in this two sample setting, we do it in terms of the difference between the averages. So we want to define here the quantity delta, the difference between the averages. And I'm actually going to just switch out my notation here a little bit, because in the problem we use mu sub x and mu sub y later on. So mu sub x is the mean yield strength of cold rolled steel, mu sub y is the mean yield strength of galvanized steel. And we want to look at the difference between the two. Now, you could set up this difference either way. You could set it up as mu y minus mu x. Ultimately, that's not going to affect your conclusion. It may, affect the sign of something along the way, but you end up with the same p-value. The reason I'm doing this is to be consistent with the confidence interval we want to calculate at the end of the problem. Just fix this. Okay, so we are going to test a hypothesis saying that the average difference is 0. That's saying there's no difference. It's the same as saying mu x and mu y are the same. And we want to test that against a general alternative. So that just means a two-sided alternative. Next, we want to calculate the test statistic for this problem. Now, we've identified that we will use a z-test, and the formula for that is delta hat minus delta naught over the square root of sigma x squared over m plus sigma y squared over n. So we need to know what our delta hat is in this instance. And that's just the observed difference of means. So in this case, for cold rolled steel, a yield strength of 29.8, and for galvanized steel, a yield strength of 34.7, this ends up being negative 4.9. Our delta naught, the value under the null hypothesis, is 0, and I know my variances for cold rolled steel. The variance is 4, and sample size is 20. And for galvanized steel, the variance is 5, and the sample size is 25. So if I do a little bit of simplification there in the denominator, I end up wanting to evaluate the square root of 0.4, and if I calculate the value of z observed now, I'll get 7.748, negative 7.748. So there is the value of my test statistic. Next, I want to calculate the p-value of the test. Now, because my alternative is two-sided, I need to calculate a two-sided p-value, right? I want to look at both the negative and the positive equivalence of my test statistic, and I want to find the area to the left of the negative value and to the right of the positive value, which in this case, we can just calculate as 2 times the normal CDF at negative 7.748. And if you go and evaluate this, to whether you're doing to 3 or 4 or 5 decimals, you're going to end up with a p-value of approximately 0. So we want to now state our conclusion at the 1% level of significance. So our p-value of 0, we're comparing that to a significance level of 0.01. P-value is less than the alpha level. So small p-value means you're going to reject the null hypothesis. Just make sure ultimately you want to take your conclusion one step further. You don't just want to say reject or do not reject. You want to state what the implication is. So here, if the null hypothesis said no difference, so we are rejecting the hypothesis that says no difference, which means what? It means that we are concluding that there likely is a difference. So you would formulate a statement that looks something like, the sample evidence suggests that the 2 types of steel do have different yield strengths. writing a conclusion in the context of the original problem is one of the most important things that you are going to do with any hypothesis test. So yes, if you have a problem like this on a test or an exam, the calculations are important, but close to probably like 1/3 of the points of the problem will be allocated to writing down a proper conclusion. So you want to make sure that you are doing that correctly. Now, alternative to doing a formal hypothesis test is to construct a confidence interval. So part E here is asking us to construct a 99% confidence interval for the difference in means. So our formula for that will be delta hat plus or minus z of alpha over 2 times square root of sigma x squared over m plus sigma y squared over n. And for a 99% interval, the z value we want to find is z of 0.005, and that value is 2.576. So now we can just plug in all the values that we've already calculated. We know delta hat is negative 4.9. We have our z value of 2.576. And then the quantity, at least inside the square root, I earlier calculated as 0.4. So negative 4.9 plus or minus 1.629 gives me a 99% confidence interval ranging from negative 6.529 to negative 3.271. What value inside the confidence interval would be consistent with the null hypothesis? A value of 0 would be. So I know the question didn't ask this, but I'm just adding this as an addendum, how you would do inference here. Since 0 is not inside the 99% confidence interval, using this approach, we would also reject the null hypothesis. And this would be at the 1% level of significance, because that is what matches up with the confidence level. So I'll pause here for a moment in case anyone has a question about this problem.
Would you mind explaining again how you determine the null hypothesis from the problem?
Yes, so let's talk through that again. So in this specific instance, the problem says we want to test a null hypothesis of no yield strength difference. So our null hypothesis that we want to test says there's no difference on average between the two types of steel. So the mu values, they represent the average yield strength. So if there's no difference, that tells us the two averages should be the same. But when we're doing two sample inference, we're always going to base it on delta. So delta is the difference between the two means. And if the two means are the same, then the difference between them would be 0. So that is how I find the null hypothesis in this case. And what I can say, I'll at one point do one example that deviates from this, but when you're doing two-sample hypothesis testing, in most instances, the value for delta under the null hypothesis is going to be 0, because most of the time you're trying to determine if two populations differ on average or whether they're the same on average. So that's what it will look like most of the time. So if you're not seeing an explicit value that says, oh, you believe the difference is 3 units, or in this case, we believe, you know, cold rolled steel is 5 KSI weaker than galvanized steel. That would give you a specific value to use under the null hypothesis. If you don't see that, you look for the key phrase no difference, and that tells you 0.
When you're doing the x minus y to look for delta, does that matter which one goes first?
No. In general, it's not going to matter. So the only reason I set it up the way I did here is in part E, the confidence interval asked for is for mu x minus mu y. So I was trying to be consistent with where I'm heading in the problem. But let's just talk through what would have happened here if you'd set it up differently. Like A through D shouldn't make a difference. You would have said y bar minus x bar, so you'd have found a delta hat of positive 4.9. So the only thing that would have changed in your z observed would be the sign. You would have gotten positive 7.748. But because you're doing a two-sided test, the p-value would end up being exactly the same. You would still find a p-value of 0 because you would still be using the same bell curve as a reference, the area to the left of the negative and to the right of the positive value. So unless the question specifically steers you in setting it up one way versus another, it's not going to matter whether you do x bar minus y bar or y bar minus x bar, as long as you are consistent with how you then do the intermediate steps of the calculation. So I think on that note, probably helpful to look at 9.2, because here is one where you could set it up either way, but you have to be very cognizant of how you formulate your alternative. Let's take a look at this example. Here it's looking at research that studied the diets of teens in the US and whether they have sufficient access to healthy food or how food choices affect their health. And so the researchers are trying to compare two groups of teens, those who eat fast food more than once a week and those who eat fast food once a week or less frequently. So for simplicity, we're just going to call these groups no and yes. Yes for those who eat it more than once a week, no for the other group. And so the researchers took samples from each of these two populations, 663 teens in the no group, 413 teens in the yes group. And what they then collected beyond that is had each of these teens run at a speed of 5 miles per hour and measured how long it took their heart rate to exceed 160 beats per minute. So you can see here in the no group, on average, it took 42.5 minutes before their heart rate exceeded that threshold. In the yes group, it took 39.2 minutes. So it happened a little bit faster in the yes group. But the standard deviations associated with those observations are also pretty large, highly variable data. Now, part A says the researcher believes that teens who do not eat fast food, so this would be the no group, will perform better on average. So the null hypothesis is always going to say, well, let me take a step back. The hypothesis here that the researcher is interested in is showing that one group performs better than the other. But there's no specific statement saying how big that difference is. So again, that's just a directional statement that tells us what our alternative is going to be. Our null hypothesis will be a statement of no difference. So again, just because I have my, in part E, a specific quantity I want to find a confidence interval for, I'm going to set it up in the same way here. So my null hypothesis, if I define delta to be mu no minus mu yes, then my null hypothesis is that delta is equal to 0. But now I have to pay attention to how I set up my alternative, because what the researcher is trying to show is the no group will perform better than the yes group. And so if I think of that as a difference now, mu no minus mu yes, that difference should be greater than 0. So if you had gone into this problem, if you had set up delta as mu yes minus mu no, then your null hypothesis would look the same, but your alternative in that case would go in the opposite direction. So the way you define delta here is important because that determines what your alternative hypothesis looks like. And the alternative is eventually going to affect how the p-value is calculated. So once you get to a p-value, it'll be the same number regardless of which approach you took. But again, the signs in the intermediate calculation may look slightly differently. But there we have our null and our alternative hypotheses. And we are hoping to use a z-statistic. Now, we have no mention of normality anywhere in this problem. So we know whatever we do, it's not going to be an exact calculation. But what we do know is if we look at the two sample sizes, both of those are greater than 30, much larger than 30. So by the central limit theorem, the normal approximation will be valid. And in this case, because the sample sizes are so large, I would even expect that approximation to be very, very accurate. But of course, we have no way of assessing the accuracy. We can just rely on invoking central limit theorem because the sample sizes are large enough. But so we can use a z-statistic because sample sizes are large enough for the central limit theorem to apply. So our test statistic in this case is going to be delta hat minus delta naught over, and now because we don't have population variances, we're going to use our sample variances, but that doesn't matter here. Whether or not the population variances are known doesn't matter if we're using central limit theorem as an approximation. So this would be the variance of the no group over that sample size plus the variance of the yes group over that sample size. Now our delta hat, that's going to be 42.5 minus 39.2. Under the null hypothesis, the difference is 0. And my two sample variances, 28.1 squared in a sample of 663, 25.3 squared in the sample of 413. So punch all of that into your calculator. And what you should get as your Z observed value is 1.993. So now we want to calculate our p-value, which relies on how your alternative is formulated. Alternative says the parameter is greater than 0, which means we want to go and find the area to the right of the value that we've calculated, which means p-value here is going to be 1 minus the normal CDF at Z observed. So you're just going to use normal CDF lower bound is negative infinity, upper bound is is 1.993, mu is 0, and sigma is 1. And this ends up giving you a p-value of 0.023. So what is our conclusion in this instance? Our p-value of 0.023, we're comparing that to an alpha level of 0.01, and the p-value is larger than the alpha level. So that means since the p-value is large likelihood that the null hypothesis is true, so we do not reject the null hypothesis. Again, conclusion after this is really important. If we do not reject the null hypothesis, that is where the sample evidence steers us to still assuming that the null hypothesis is true. So the sample evidence suggests the two groups do not differ on average. In other words, on average, it takes them the same amount of time before their heart rate exceeds 160 beats per minute. So make sure to state your conclusion in the context of how the problem was formulated. And then to finish this out, we again want to construct a 99% confidence interval. So our delta hat is 3.3. Our confidence interval is, or our approximate confidence interval is given by this expression. And so this will be 3.3 plus or minus same Z value as in the previous problem because we're doing a 99% confidence interval. So this is 2.576 and under the square root we have 2.741. So if you finish out this calculation, you'll get confidence interval ranging from -0.965 to 7.565. And in this case, since 0 is inside the 99% confidence interval, it says we do not reject the null hypothesis at the 1% level of significance, just to show you the consistency between the two. Now, does this mean that there really isn't a difference? I think that's maybe one question worth just talking about for a moment. No, that is, at the end of the day, that is not what our takeaway can be here. Our takeaway is that it's highly unlikely that there is a difference because we've collected a pretty big sample in each case, but we could have made an error. In this case, since we're not rejecting the null hypothesis, it's plausible that we're making, or possible rather, possible that we're making a type 2 error. And in fact, if we look at our confidence interval, the confidence interval gives us a whole range of values that would be consistent with the data. So the confidence interval says, yes, it is possible that there's no difference because 0 is inside the interval. But on the other hand, you know, the right endpoint of the confidence interval, 7.5 minutes, it tells us, you know, still consistent with the data, is that it takes the non-fast food group 7.5 minutes longer on average before their heart rate exceeds that threshold. So the formal hypothesis test says there's no difference, but there are potential values of difference that are also consistent with the data. Statistics, whether you're doing a hypothesis test or a confidence interval, it never allows you to make an absolute definitive statement because we're always recognizing what the tolerance thresholds are. We can only make statements with certain degrees of confidence. So that's why the confidence level or the level of significance is so important in how everything gets formulated.